Looks like I'm recording, which is what I want. Nice to see you all. I'm going to talk about some cool things like lists today. Let me share my screen, and we'll also use the document camera a bit later. Feel free to ask me any questions as we go, as always. I don't always see the chat when I'm not actively engaged in being social, so feel free to bring it to the attention of the TAs or to shout out a question. Happy to talk with you all. Okay, so I believe we are successfully recording, and I will start with a little bit of introduction. So first announcements, short assignment 4 has already been due. The extra credit part, if you would like to do it, it's not due till Friday. Essay 5's due on Friday, and problem set 2 is due a week from today. So today I'd like to talk about lists, hierarchical data trees, and so forth. Let me kind of put this in context a little bit. So first of all, I wanted you to see something about lists, and so one point of the assignment due today was so that you could get a little bit familiar with reading the textbook and trying them out, because I wanted you to see what was going on for yourselves and then help reconcile that with how I think of lists. And one of the reasons for this is that while you may have seen linked lists before, it's my view that they are incorrectly implemented in most languages and incorrectly taught in most data structures class. And so this is kind of the, I think, the clean way to do this. So today, one of the things we're going to do is we're going to have the ability to build data structures based on trees and lists and things. This will also make things more interesting. Up to now, basically, we could only prove things about functions that involve numbers or functions that involved other functions. And that's because we didn't really have data structures, but now we do. One thing I'll mention is that we do have to add more primitives, but no new special forms for today. And those will be in order to make and manipulate lists. Now, one thing I'll also mention is that if you are confused about anything or want to talk to us, please do. There are many office hours and recitations to do that. And also, I want to mention that I stay around after this to answer questions and have general discussions with anyone who wants to stay. So please talk to us if you'd like to do that. So lists in this form are super important. They're a data structure. They formed actually the basis of modern artificial intelligence. And they're rather classical in computer science, which means they've been around a long time and survived the test of time. And I learned about them a while back. In fact, it got me interested in AI, where I did my PhD work. And in honor of that, I'm wearing the same shirt today that I wore when I learned about these things. It's maybe a little bit tighter, but not too bad. And reminds me of the good old days, which are still the same days today because lists have survived in most languages in this form. So to put this in the context of the class, we have 3 pillars on which to be able to talk about programs rigorously. So we have induction, of course, which lets us talk about whether recursive and iterative processes are correct. And we had higher order procedures, which are essentially control structures. And I'll be explicit about this when I introduce the map procedure later on in this lecture, also in the textbook. Map is probably my favorite function in Scheme, or one of my favorites. And we invariably ask a question about map on midterm 1. And second favorites include reduce, which is called accumulate in the textbook and in this course, but Google programmers call it reduce. And later I'll give you a lecture, or in lecture 14 on map reduce, a paradigm for parallel and distributed programming. So basically with these 3 things, higher order procedures, which give us our control structures, and this means we do not need constructs like while, loop, do, and for. We can use them with higher order procedures. Once we have data structures after today in induction, then we can prove programs are correct and efficient. In other words, we can do the same kind of proofs we've been doing, but for things that manipulate data structures, lists, trees, and hierarchical data, which is pretty cool. So let's get started. A journey of 1,000 miles begins with a few steps. There's some really good reading. You've already been thinking about that. One of the cool things today is we're going to talk about some procedures that are primitives but are not constant time. And this is super important in powerful languages like Scheme and Lisps. Often you can do something very powerful but also very expensive by calling a primitive. And you need to know how expensive that is and factor it into your analysis of algorithms. So lists are unbelievably useful elements. They're basically ordered sequences of stuff. You've seen them. They have a first and second element and so forth. And the length is not restricted. Make them as long as you like, which is pretty cool. So I mentioned we're going to have abstractions here. So we have the abstraction as follows. So we have a constructor which is called cons for a constructor. And it takes as input an object and a list, and it returns a list. And basically you think of it as adding an element to a list, but there's no destruction or modification in functional scheme. It returns a new list with the object const onto the front of it. Now, once you have this data structure, you can get at it using selectors, namely head, tail, and null tells you whether or not you have an empty list. Now, there are alternate names for head and tail. We're not going to get too wound up about this. Head and tail are sometimes called first and rest, if you want to sound cool. And in some languages and some instantiations are called car and cdr because they were implemented as parts of two words in early implementation of these languages. So head, first, car, tail, rest, cdr, all synonyms. Now, when we have these things, we have a contract, i.e. a mathematical statement providing the equivalence of a scheme statement and some expression, and it works like this. Look down at the contract here. So if you take a list L and you cons X onto it, you get a new list. If you take the head of that, you get X back. The symmetric case of that is if you take the list X, so you take this L and you cons X onto it, and you take the tail of that, you get L back. And that's the only thing that head and tail have to satisfy. Finally, the null function, which is a predicate, is true if and only if L is the empty list, which indeed is written like this, single quote and two empty parentheses. We'll have lots more of this later and in section, and we'll try to rationalize this. Now, we don't say what head of the empty list is, and we don't say what tail of the empty list is. These are undefined. In some versions of Lisps and Pythons and Javas, they do return a value. You can't count on that. So if you write some scheme function, move to a different version of scheme, might return something else. So don't ever take the head or tail of an empty list. Okay. So lists in scheme are built out of pairs of two things. So pairs are a familiar concept to you. For example, if you want to think about plotting things in calculus on the real line, you have a pair x, y, which corresponds to a point in the plane. So a very natural mathematical object. And there's a concrete implementation of these too. So there are three different ways that cons, head, and tail are used in scheme. They're so-called, and I'll explain these, proper lists, pairs, and structures that combine the two. So what are these things? And of course, proper is probably the thing that we really want. So I would phrase this like this. So what does it mean for a list L to be a proper list? So I like to think of it like this. We saw repeated before. Hopefully you did the exercise and you wrote repeated. So a list L is a proper list if there exists some integer n, such that if you take repeated tails of the list, you eventually get the empty list. If you eventually get anything else, which would be called an atom, it's not proper. So repeated tails eventually give you an empty list, otherwise it doesn't. And notice we have this terminology now. We have some mathematics like there exists. We have the notion of a higher order functions like repeated. So we can very concisely write down exactly what it means to be a proper or improper list. But I've also said it in words here if you like that. Okay, so there are really two types in scheme. Pairs are anything that can be taken apart with head and tail. And lists include the empty list, and they also include the any pair whose tail is a list. I'm sorry, I just got a call on my phone, and usually that screws up Zoom. Can you all tell me if you can still hear me?
Yeah, we can still hear you.
Yeah, I'm really sorry about that. Thank you. I'm going to actually turn off my incoming calls here, if I can, and come back to you. Who calls anymore? I mean, what's that? Like getting a message from 1987 or something, but geez. All right. Can you still hear me?
Yes.
Yes.
Okay, good. Thank you. Sorry for all the hassle. Okay, so pair, you can take them apart with head and tail, anything. List is an empty list, or it's any pair whose tail is a list. And that's how the type checking actually works here. So let's do an example of this. So if I say define A to be the cons of 1 and 2, I make a pair whose head is 1 and tail is 2. This is not type list because the tail is not a type list, right? So recursive definition. The tail is 2, in fact. But if I do this thing here and define B to be cons 1 onto cons 2 onto cons 3 onto the empty list, I get a thing that is in scheme. It's both type pair and type list. This is actually a proper list. And the reason is that the empty list is a proper list, and so is cons 3 onto it, and so forth. Now, there's many ways to implement pairs and lists in scheme, but there's a sort of a diagrammatic representation that we use. Now, the diagrams are not a proof, but they're a nice way to visualize these lists. So let's look what happens using what's called box and pointer notation, and I will show you what happens here. So what happens here is we get a list that looks like this. Obviously, we do it inside out. The first cons gives us a cons pair that looks like this. We have a 3 as the head and nil, or the empty list, as tail. The next cons gives us a cons pair like this. 2 is the head, and the tail is this box here. The final cons, or the outer one, makes a cons pair like this. The head is 1, the tail is the rest of the list. And B, when it's bound, points to this guy here. So here's some crucial points. Useful fact, very useful on tests. Cons always builds exactly one box. So if you want to see the storage requirements of your algorithms, count the number of conses. Now, note in this diagram, the pointer points to the entire box, which is an object, doesn't point to just the front half. So each call to cons builds another pair box. It's distinct from all their pair boxes known by your program or that you'll ever see in the future. And that's really what functional programming means for data structures. So when we draw an arrow that points to a box, it represents a pointer to the entire box. Again, not just the head of it or the tail of it or something like that. So this is, in some sense, you can think of this as a concrete representation of the list 1, 2, 3, which is pretty cool. Now, here's a cool thing. If you evaluate B, it prints out like this, 1, 2, 3. And that looks a lot like scheme expressions, a whole lot like scheme expressions. This is completely intentional, and this is why it's so easy to write scheme programs that manipulate other scheme expressions. And in fact, even today, people prototype languages in scheme and list because it's an incredibly fast way to make compilers and interpreters. Okay, so now we've seen lists, linked lists. Notice we never had to think about pointers, never had to allocate them, deallocate them, think about memory. All that's taken care of automatically for you by scheme. Okay. Now let's go ahead a little bit. So yeah, in SICP, you can actually write a scheme interpreter entirely in scheme, and you can do that within the span of like 3 weeks. So pretty cool. But this isn't per se a programming languages class. It's really a theory, it's a mathematical computer science class. So we're going to just sort of say that in passing. So there are a ton of useful operations on lists, so-called list operations. And let's look at one of them. So list here, this is a procedure that puts all its arguments in a proper list, which is pretty neat. Okay, so that's kind of nice. And let's look at an example. Here's list applied to 3 arguments. The first is plus, the second is 27, the third is plus 2, 1. And this returns a list that looks like this. It's got a procedure object in the beginning, and it's got a 27 here, and it's got a 3 here. So this is kind of strange. It takes an arbitrary number of arguments, but they're all evaluated. And, you know, it takes any number of arguments, which is pretty cool. I've shown you how to do that in a handout today. But suppose we wanted to do this to actually build scheme code. Like, in other words, we wanted something that looked like this, not the procedure object add, but the symbol plus. What if we wanted to do this? So what we want to do is we want to kind of turn off the evaluator temporarily in order to do this. So I want to mention that this isn't just an issue with programming languages, it's a deep, actually kind of linguistic problem. And to illustrate this, actually, I would like to ask for a volunteer from the audience to do a quick experiment with me to illustrate this point. Who would like to do something? I promise no animals or people will be harmed in this experiment, and it will be brief and not embarrassing.
I can.
Okay, great, Caroline, that's fantastic. Okay, so I'm gonna give you a little instruction. Imagine you're, a computer, and then I'm gonna give you a second instruction. Okay, so please say your name.
Carolina.
Okay, that's excellent. But if you look at me now, I actually meant something else. Could you, not Carolina, could you say your name in quotes?
Your name?
Yeah, there you go. So there are two ways of answering this. Thank you very much. Let's have a round of applause for our volunteer, Carolina, which is great. Well done. So going back to where we were before, you see the difference here in thinking about this, which is that, obviously Carolina's name is Carolina, and I said, say your name, and she very reasonably said, Carolina. Fantastic. The thing is that what if I wanted someone to say the string or the phrase your name instead in quotes? So we need a form of quotation to tell the interpreter, hey, don't actually eval this. It's like an anti-evaluator. So we've actually seen this on symbols, right? And we know we're going to use it more. So quote stuff means just return something that prints like stuff as a value. So if we take plus and evaluate it, we get the procedure add, but quote plus evaluates to the symbol plus. What happens when we evaluate x? Well, it depends. Like if it's undefined, we get an error, otherwise we get some previous value, but quote x evaluates to the symbol x. Similarly, plus 1, 2 evaluates to 3, but quote plus 1, 2, that evaluates to a list of 3 elements, which prints as plus 1, 2, like this. So this helps our immediate problem. We just say list quote plus 1, 2, and we get back the list plus 1, 2. Incredibly useful. And notice that list, there are no special forms going on here. So if we say something like let A be 3, list quote plus A2, we get plus 3, 2. Everything gets evaluated. So list is not a special form. So this is pretty neat. Now you may be asking, this is really weird, one single quote? Like I'm sort of like Sheldon Cooper on The Big Bang Theory. I want to close that other quote, right? But it's not like that. The way the designers of Scheme thought, you never need that close quote. Why have any syntax we don't need? So we don't actually need the close quote. We just have the first quote. So it means turn off the evaluator for this expression. So incredibly useful. So the elements of a list can be absolutely anything. So here's an example here, and we'll actually kind of draw this out. Look here, I take list applied to, quote plus, then another list and so forth. And this prints as follows. Let's try to, if you will, I wouldn't say prove that, but argue that by drawing the box and pointer notation. I'll just do that right now. So what is returned here? Well, list is going to, this first list is going to make 3 elements. It's going to look like this. So the first element here, this has a star in it. The tail then points to another box here, which is going to be this thing. The third element is going to have a 3 in its head, and then a nil. What's this thing here? Well, that points to the internal list here, another list. Remember, it points to the head. I'll draw it like this. That's another list of 3 elements, like this. This thing here, what is it going to be? This is going to be a plus. This here is going to be a 1, and that's going to be a 2. And that's going to be the empty list. And we return a pointer to this entire thing here. So that's 2 ways of seeing what happens here. So if we evaluate this, we're going to get something like that prints like this. And this is the internal representation, which is a nested list as you can see it. So again, an important fact, very useful on homeworks and tests. A call to list with n arguments builds exactly n boxes. So here we have 2 calls to list. The top one has 3 arguments. The inner one has 3 arguments, so we make a total of 6 boxes. But you can draw out the box and pointer representation to see exactly what the data structure will look like. Okay. So pretty cool. We could do lots with lists. Really neat thing. So again, it's a list of 3 elements. The second element is itself a list of 3 elements. Okay. Good time for a drink from the Lambda mug. Which at the request of my TAs is decaffeinated tea rather than caffeinated. So let's do some cool things with lists. Finally, the much beloved length function. All right, so how long is a list? So it's one of those basic things you can do here. This is a scheme primitive. Let's see how it could be implemented. So we write a function like this. If the list is null, we return 0. Otherwise, we add 1 to a recursive call to length on the tail of the list. And this will give you the length of the list. So key question here. What's the running time? Suppose we have a list L and its size is n. What's the running time of the length procedure in terms of n, or the size of L?
Would it just be n?
Yeah, it would be n. You know, I would rather we said order n, because it's not exactly n. Do you see why I say that, Vanessa? Does that make sense?
Yes.
Yeah, because we have all these constants here, right? We have to check for null, 0, plus, all that kind of stuff. All constant time operations. So run it order n. That's expensive, right? You have a long list. I mean, you know, even when I was like, you know, an undergraduate or master's students, I had lists that were like, you know, 10 million long. So just to find out the length of a list takes 10 million amounts of work. That's a lot. So be careful about length. So this is a function that is not going to be, you know, that fast to do. So again, we can ask more questions about this. What kind of process is it? It's obviously recursive. Can you write a tail recursive version? Can you prove that this is correct? So that's something we actually can do now, but we'll show you some better ways to do it in a couple of lectures. So let's look at some examples here. So we have length of the list 1, 2, 3 is returns 3. How about this one? Do you understand why this returns 3? Let me know if that makes sense or if you're confused. Is that clear? Does anyone have any doubt that will return 3? Like, why doesn't it return 4?
Because there's only 3 actual elements, 1 number, 1 pair, and 1 number.
Yeah, that's right. I mean, basically, that's exactly right. At the top level, there are only 3 elements. So it just counts the number of tails, exactly as you said. Now, can you count all the things going down the tree? Yes, there's a way to do that, but length doesn't do it. So the main thing is this is not a constant time primitive, right? It takes order n time. So pretty cool that we can see that already. All right, so now we have length and an argument that it's linear time. We know that we could prove this length function is correct. We know we could write it, so we can use this.
We have a quick question.
Yeah.
So you're in the second length example with that sort of nested list. There was a question, why don't you need an additional quotation mark before the 2, 3 sublist?
Because the whole thing is quoted. So the quote means, give me something that prints exactly like this. So if I had an additional quote, I'd have to do an additional val to get it. So it's just not required because you're quoting the entire expression. So quote works on anything. It says don't evaluate this. And the thing not to evaluate is the entire list. So in some sense, you know, it doesn't even need to look at it. Okay, more questions? Sure, thank you. All right, let's do something else. We'll go on to my favorite function. So as it turns out, and it's hard to decide. It's like your children, right? Which one is the favorite, right? But it probably is my favorite. Don't tell the other functions. So very often we want to take a function and we want to apply it to each element of a list and return a new list of that result. So it's a very common paradigm. I have a list of values. I have a function f. I want to take everything in the list. I want to f it, and I want to make a new list in the same order of the f'd values. How can we do that? Well, a high order procedure. So there's a scheme primitive for this. which is really nicely implemented, but let's see how we could do it ourselves. And that's the map function. So map with F, map F list applies F to every element, returns the result. So here's how we would do it. I'm going to take this to the next page. Don't get too much vertigo because I'd like to, elaborate a little bit. So I've just written the function here myself. Here's our map function. Look what it does. It takes in a function F and it takes a list L. If the list is empty, it returns the empty list. Otherwise, what does it do? Get the head of the list, F it, cons that onto the result of mapping F over the tail of the list. So very nice. We can meditate on this a little bit, but let's think about it. Here's 2 examples. I'll show you one first. So suppose we have this weird thing here. We have this list of lists, and we take our length function and we map it to find the length of the list. So intuitively, this does the right thing. It tells you, if you give it a list of lists, what is the list of lists? A list of length 1, then a list of 2, 3. It gives you the lengths over here like this. So in other words, this computes the length of this list, this one, conses them up into new list of lengths like that. So that's pretty neat that you can do that. We've already used our 2 functions. Here's a paradigm we'll see a lot. Suppose we have a list, in this case, the list 1, 2, 3, 4. And suppose what we want to do is we want to conceptually add 2 to every element in the list. Remember, we can never change a value in functional programming languages. What we mean by that is, and what I should say to be more explicit, is return a new list, which is the result of taking the input list and adding 2 to each element. So look, I have an anonymous procedure here. This procedure is going to take any value and add 2 to it. I'm going to map that over this thing here, 1, 2, 3, 4, and I get back 3, 4, 5, 6. And of course, there are no new paradigms here, so you can actually prove that this is the result. You can prove this happens, is correct, using induction and the substitution model. So very powerful to be able to take lots of things in a list and F them. So the way it works essentially is we go down the list taking successive tails and we cons up or build the resulting list. And like length, it operates element by element, not on the primitive elements. And that's an example here. Notice it's taking the length of the list, it's not going down into the lists. And notice that map is also a non-constant time primitive. So what is the complexity of map? What would this be? What do you think?
Is it also order n since you're going down the list?
It certainly is. Certainly order n is a pretty big component of it, right? Because it has to go down there, but it's got other things in there too, like how much time does F take, right? So, F could be something really fast, like lambda n plus n2, which is constant time, in which case your answer is exactly right. But in the case of length, it's a little more subtle, right? So in some sense, it's going to be the product. I mean, conceptually, it's the product of the n, just like you said, and the time for F to do its thing on each of the sublists, right? And even in this example here, you can see that that varies. Like there's one list that's like 3 times as long. So in some sense, it's the product of the n, which is always there, and the time to do F on each one. So conceptually, here's how I could think about it. Sort of approximation would be the time would be something like this. I'll write some things down here. I'll write down here instead. So the time complexity might be something like this. Order n, exactly as you said, so good job, times something like order g of L, right? Where this is the time complexity for F. This isn't quite right? It's just the right idea because F takes different times depending on the inputs. Like here, it ran in time, proportional to length 1. Here it takes 3, and so forth. So really, what we have to do to get the complexity here is something like this. And I just want to show you that even though everything that we show you when you first get a concept is like unbelievably simple, even though it's still hard, solving real problems sometimes requires something that's a little more complicated. So the way I would probably do this, I'd say something like this. I'd say, so I'm looking at something like this. I'd say let Li be the ith element of list L. And I'd say let Mi be the size of Li. I don't really like this notation, but people use it in computer science, so we might as well. And then we might say let big M be the maximum over all i's of the M sub i's. Then the running time of this, although it's not really an order notation, is something like the sum for I equals 1 to n of the function g, which is the resource function for how long f takes on the size of mi, which is the size of the list. And that's bounded above by order n times g of big M, which is the max. So, it's hard to get at the exact complexity, but you need a dependence on n for sure. And you need some recognition that f can take longer on longer lists. So this is kind of a messy expression. It says it takes as long as it takes, right? Obviously there are n components here because we're summing over n things. But what you have to do is you have to sum up the time that f takes, the function f, on each element here, and that's g of mi. So to get a bound for that, you could just say, well, what's the biggest one? We'll let big M be the biggest one of those. Obviously, I can substitute that and get an upper bound. So an upper bound of the complexity is order n times the time that f would take on the longest list. So to reify that in our situation here, basically, the complexity here would be something like order n times order m, where m is the longest list. So the key thing you should realize here is there's a double dependence, one on the length of the list, which is always linear, and one on how expensive your function f is. And if this seems nitpicky, think of it this way. I could either put in an incredibly simple function like adding 2 to every element, or I could put in some really horrible expensive function that ran for a long time. Okay. All right, so that's the complexity of map. Let's do a little bit more. How about another function? Here we have some comments. So here's a copy function. Pretty interesting. We use map to copy a list. So the key thing here about this is that what copy does is it basically returns something that looks like the original list, but it's a copy of the thing. So what you should convince yourself here, because it maps this simple function, which just returns x over the list. So the way to think about that is L, when it's called, is bound to something that looks like this. I'll use a list of 3 elements. And why? Because we're looking at this example here. So our list of 3 elements looks like 1, 2, and 3, empty list over there. And what it returns is the following thing. Like it's going to work inside out here. What it's going to return is a list that looks like this. It's going to have 3. It's going to have a 2. It's going to have a 1. And this is what is returned from the function. So it's an exact copy of the list, but it's not, in some sense, the way to think about it, doesn't share the same storage location. So if you used a function in Scheme called equal, it would tell you that these objects were equal under this function because they print the same. But the thing is, there's another function that asks, are they actually the same object? Do they store the same, are they stored in the same location? This will return false because these are different storage locations. So we've returned a copy of it. With a functional program, you cannot distinguish between a copy and the original object. If I have side effects, I can. And the reason, and we don't have side effects, but the reason you could tell is that I could go in, I could change one of these things. So for example, I could do something like this. I could say, well, I don't really like that. I'm going to change this to be some other value. For example, I could take this guy here, and I could change that to be a 77. And then the original list is changed, but the copied list is not. So as soon as you have assignment, the semantics that copies of things cannot be distinguished from the original goes away, and we have to use something other than the substitution model. But fortunately, we're not going to use assignment until lecture 24, so you don't have to worry about it. So this is interesting about copy. We can make a copy of an object. It's stored somewhere else. We can't tell the difference unless we have side effects. Okay, so one thing we want to be able to do is prove these functions are correct, things like copy and things like length and things like map. And we'll use some form of induction. You can actually do that now, but I'm going to show you some affordances. Side effects would be any kind of assignment or any kind of changing of a data structure, and we don't allow them. Functional programming doesn't allow them. Basically, programs with side effects can't be parallelized. Or they can if you have a team of engineers to do it, but they can't be done by a mortal. Okay. So now let's do something else on list. I want to put some lists together. I want to append two lists. So conceptually, I want something like this. I want to pass in a list 1, 2, 3 and a list 4, 5, 6. And I want to get back a new list 1, 2, 3, 4, 5, 6. And this is a scheme primitive, but let's see how we could implement such a thing. And it's a little bit surprising, right? I want to go through this. In fact, I want to do a little proof. But one thing to meditate on while I move over to the document camera is that in some sense, L2 doesn't even get looked at, right? It kind of just gets passed along here. So this is kind of a peculiar object, but very powerful. So I think, to understand this, it's not really sufficient to kind of write in the margins. And I'd like to do a little, you could call it a trace or a little substitution model exercise and a box and pointer model exercise to see how append really works here. So let's take a 30-second break. I will move over to the document camera and we will continue in a moment. Okay, I should be back at the document camera. I wonder if you could let me know if you can see the paper and the code and if you can hear me.
Yes. And one quick question.
Yes?
There's a question, is modifying values possible in functional programming?
No.
Thank you.
Not only is it not possible, but it's not necessary. You don't gain any power by modifying values. The things you can compute with functional programming are exactly the same as the things you can compute with side effects. Now you can make copies, you can make new values, all you want, but you can't change value. And I should also mention that if you added that, by the way, Scheme does have that capability, but we don't let you use it yet. If you do that, then the substitution model breaks, and you need a new model called the environment model, which is actually a very nice model, but it's not nearly as easy to understand and use as a substitution model. So it's harder to prove things about your programs. Okay. And as I mentioned, automatic distribution and parallelization basically goes out the window, or it becomes a PhD level topic, how to parallelize and distribute your programs if you don't have a functional programmer. Okay, so we have this creature here, which I've put in, pointer drives me absolutely bananas. So we have this creature here, append. We'd like to kind of understand what's going on. So we have two tools to get at this now, right? We have the substitution model and we have box and pointer diagrams. And I would like to kind of go through that a little bit, see what happens. So let's do substitution model first. I'll just do some of the, probably just the eval steps and see what happens here. And let's look at this thing here. Let's look at this append. Just kind of trace through with substitution model. You can view this mathematically as a proof or the sketch of a proof that this statement is true, namely append 1, 2, 3, and 4, 5, 6 returns this list here or equals this value here. So let's look at this. I'll start like this. So my goal is to do this and then at the end do the box and pointer diagrams. Not the end of the lecture, the end of the example. So append 1, 2, 3, 4, 5, 6. Let's look at the code. Obviously L1 isn't null, so we come down here and we have a cons and a recursive call. Obviously this is written as a, obviously it's syntactically recursive procedure. So what we're going to do here is we're going to obviously be creating a recursive process. You should of course be asking yourself, okay, so Bruce proved that for these two lists, but can I prove in general that appending two lists returns the correct list? How could I write a tail recursive version? How could I prove what the complexity is? Okay. So expanding this, we now have the cons statement. We have and a recursive call. Let's see what that is. So this then expands to what? Cons. And we have an evaluated 1 here onto a recursive call to append. We have the list 2, 3, which has been evaluated. And we're appending that onto the list 4, 5, 6, which has been evaluated. All right. Next time, pattern repeats. We have cons 1 onto cons 2 onto a recursive call to what? Well, we have just the list 3, which has been evaluated, and we're calling append on that, and of course the same list 4, 5, 6, which is never really touched or modified by the append procedure. Next time, again, L1 is not null, so we have cons 1 onto cons 2 onto cons 3 onto a recursive call to append, which is now called with the empty list, which has been evaluated, and 4, 5, 6. Now at this stage, we're going to bottom out because list 1 is null. And look here, we're going to return L2, which is 4, 5, 6. So the next time this expands to cons 1, cons 2, cons 3. And as I said, we can see from the code here that when L1 is null, we return L2, 4, 5, 6. So now we return 4, 5, 6. So notice we have all these deferred operations. In this case, the deferred operations are not pluses, right? They're conses, but that's fine. I mean, obviously it takes linear space to do this, but now we'll reverse this and we'll cons up the list again. So obviously this statement here, this is going to return a new list which has 3 cons down to 4, 5, 6. So it looks like this. Cons 1 onto cons 2 onto 3, 4, 5, 6, which has been evaluated. Next stage is cons 1 on to 2, 3, 4, 5, 6, because that's what cons does. That should be a 6. And finally, this returns the list 1, 2, 3, 4, 5, 6, as desired. So I would regard this as a proof using the substitution model, leaving out the apply steps, but nevertheless, I think a valid proof that as desired, we have shown that append 1, 2, 3, and 4, 5, 6 returns the list 1, 2, 3, 4, 5, 6. And you might be asking yourself again the questions I said before. What's the complexity of this? Well, they're deferred operations. Obviously, it takes linear time. Linear space because of deferred operations. You should ask yourself, can I write a tail recursive version? Yes, you can. Can you prove these are correct? How would you prove these are correct? What would the strategy be? What do you think? Do you think we need any new tools? Or do you see a way that you could prove this is correct now? I wasn't going to do the proof now, but I wanted to ask if you had any idea how we would prove such a thing is correct for general lists. See, here we proved it for 2 particular lists, 1, 2, 3, and 4, 5, 6. What would you do in general in this case? What would the strategy be?
Could you assume it for any 2 lists where you kind of make the first one fixed and the second one can be any size?
Yeah, I think it's the right idea. So how would you, do you think you could, how would you show it's true of lists of any size though? Like, do you think if it works for smaller lists, you could show it would work for lists that are slightly bigger?
Yeah.
And what would you, what strategy would you use for that?
Well, if it works for a list of size n, adding 1 more element wouldn't really change the way it works. So it would work for n plus 1.
Right. And what's the name of that proof technique?
Induction.
Exactly. And I think Vanessa and Robert also got it. I saw flying by in the. So yes, you can prove this by induction. So paid commercial advertisement, you could do this exactly as you said. You can prove this is correct for any lists of any size. In fact, you have the right idea. You assume list L2 can be anything because you're not going to make it any bigger or smaller. So it's arbitrary size. And then you show that it works for a base case for L1, and then you show that it works for induction hypothesis. Induction hypothesis implies the induction step. So you can actually do this. And we can actually have the capability of doing that now. I'm going to show you in a lecture or two a technique called structural induction, which is what Vanessa's t-shirt will say shortly. I have to negotiate with a new vendor. The old vendor won't make that t-shirt anymore for some reason, but I'm working on it. I'd offer to send my t-shirt, but I think mine is too large, but it will happen. So structural induction would be a technique building on induction to do this, or you can use regular induction. So if you don't know what structural induction is, and I assume you don't, just assume this wonderful thing is happening in about a week, and be comforted by the fact that your knowledge of induction can be used to prove this right now. Now, let's go through this rather quickly and show that what happens in terms of box and pointer notations, lists and data structures. So this isn't a proof, but it's an argument. It's a graphical way to illustrate what's going on, and I think you'll find it pretty cool and pretty interesting. So we're going to come back to this and just ask what happens to box and pointer diagrams. From a formal point of view, with this proof here in hand, what I'm doing is I'm animating that with pictures of the data structure as it gets modified. So here's what happens. When we make the initial call to append, we have L1 and L2, and they look something like this. So L1 looks like this guy here. It's a list of 3 elements, 1, 2, 3. And of course, L1 just points to this guy here. And that's what it looks like when we call it the first time here. How about L2? Well, it's kind of similar. Looks like this. List of 3 elements. Oh, I need my null pointer here. And what is this? This is 4, 5, 6. And L2 points here. By the way, I will have a gloss at the end of this about the concepts or questions about modifying values. Yes, Robert, these are like linked lists, but there's some differences in that you can't get into trouble. And I'll make some comments about that later. But they're essentially linked lists correctly implemented. And I don't mean that every time you saw them in the past, they were incorrectly implemented. I'm just saying that many times the things that I care about aren't addressed by other languages or implementations. So what happens here? I'm basically going to start here. Basically what we're going to do is we're going to look at what happens with this statement here. Namely, executing the deferred operations for all these conses. Because up to here, we haven't built anything. Down to this point here, all we've made is this huge stack of things that we're going to do later. It's like promises. I'll do it later, just you wait. But at this point, the recursion is bottomed out. We have to do all the operations. So what we're doing at this point, I'm going to animate this step here. So what does that actually look like? This is so exciting, we need a different colored pen. So here's my red pen. I'll start doing this. So obviously do it inside out, we cons a 3. Cons makes a new box. Let's make a new box. Here's our new box. Cons 3, the tail is this. Let's do the one out here, the cons 2. That makes a new box. Cons 2, the tail is this. Cons 1, here we go. Cons 1, the head is 1, the tail is this. And we return a pointer to this. So now we have append in all its glory. L1 is this creature here. Notice it's unmodified. L2 is this creature here. What we return is this, a pointer to this thing here, which of course is the list 1, 2, 3, 4, 5, 6. So what I want you to realize, the way this has been constructed, suppose you're writing a big collaborative program and lots of other people want to use these extremely valuable data structures, L1 and L2. No one is forbidden from doing that. Future programs and past programs can rely on L1 being 1, 2, 3, and can rely on L2 being 4, 5, 6. Even though another part of the program might have a pointer to here, and that's a sublist of this thing. Doesn't matter at all. Because I'm not allowed to change it, the programs that rely on L1 always immutably being 1, 2, 3, and other parts of the program that depend on things L2 being immutably 4, 5, 6, they are not affected in any way by the fact that I've made a new list, 1, 2, 3, that points to this and reused as part of this list. And that's the beauty of this system, is that I can do all these operations functionally, and then I still have the substitution model. Because the substitution model assumes that L1 will always be this, L2 will always be this. I can make new things if I want, but they can't change either. So that's how append works. Kind of cool, right? All right. Questions on append? So in answer to a question that I think Robert asked, these are exactly linked lists. The thing is that in some other languages, but not all, you have to worry about allocating and deallocating these pointers, and so you can get memory leaks, namely a pointer to a location that's no longer used. And that's a dangerous situation. So you can make any data structure you want in Scheme, and because it takes care of all the allocation and deallocation for you, you can never run into problems where you have a pointer to a part of memory that you're not allowed to access. So all you do is these cons head and tail operations. So cons head and tail are designed so that all your data structures are safe in two ways. One, no memory leaks. And second, you never have to change a value. Okay. All right, do you have any questions on the proof, if you will, that append applied to these two arguments returns 1, 2, 3, 4, 5, 6? General questions on append or other questions on the box and pointer notation that corresponds to this? All right, so some things to think about are, again, looking at this function, you can see that it's recursive process. Could you write a tail recursive version? Can you analyze its complexity? Can you prove it's correct? Those are the natural questions to be asking in these cases. And yes, induction and the substitution model will be the way that we would prove things are correct. And our time complexity analysis would be a way that we would infer and in fact prove that this particular function was linear in the size of list L1 and completely independent of the size of the list L2, which is kind of an interesting fact. So you could give it a list L2 that has a quadrillion elements and a list L1 that has 6 elements that it will run in time proportional to 6. Kind of a nice feature. All right. So I want to move on to some other things, but any last questions on append while I think about that?
I had a question about something earlier when you said a list called with n arguments builds exactly n boxes. Do you mind just going over a quick example? Because the one that you said it for, I didn't really understand.
Sure. Let me go back to the tablet. I think that'll be a little easier. So give me just a moment here and we'll do that. All right, let me know, can you see the tablet and can you see me?
Yes.
All right, good. So let's go back to the example here. Let's see, I'll get rid of some of these annotations. Do we have list here? All right, so I don't think we need my annotations here, so I can get rid of those. Yeah. Doesn't really want to. All right, so should we look at this example here?
Yeah, that'd be great. I think I was just confused because like what you just erased looked like 6 boxes to me, but I don't see that many arguments.
But do you see 2 calls to list?
Oh yeah, so then it's just 2 times 3.
Yeah.
Is that what you're saying? Okay, that makes sense. Thank you.
Yeah, I could draw the boxes. I could animate the boxes. That would help. But maybe that clears it up.
I think I understand it now.
Okay, good. Great question. Thanks. That sounds good. All right. I'll go on. If there are other questions, please shout them out. I'll come back down to where I was. So I've written out append, in text too, just in case there's any ambiguity with handwriting, so you can look at it. A little harder to see, I think, in text, but we'll take a look here. Now, this is a lot of stuff to think about. I mean, these examples are all pretty fun. So we're going to do some more in section and also some stuff with higher order procedures other than map. But you could also use this essentially, these structures, and even the one that was just pointed out here with list. I'm sorry to make you dizzy. This is essentially when you have two levels, you essentially have sort of a tree structure, right? Even in this case here, you know, we have a thing, I'll draw it again, where we are going to get, so when you have multiple levels, this is the pointer we return. This is essentially like a tree structure, right? It's not a very nice tree in some ways, but we can make more complicated data structures out of lists once we nest them. And that's a fundamental insight. I have an example for you here. Look away if you're dizzy. So here's an example. And this is, you know, this is just a bunch of nested lists. But in this idiom or this paradigm, it really represents a tree. And I've drawn it in two ways, like by, you know, here the limits of the ASCII character set are completely reached. I've drawn the tree out like this with sort of boxes and pointers essentially, but I've also drawn it over here kind of more the way a computer scientist would draw it. So we have a tree, it's not a binary tree, a tree like this that represents this. And here the leaves, those are nodes that have no descendants. They're all primitive objects like numbers. So you could do various operations on trees that are pretty cool. And they're very natural in a recursive functional language like Scheme. And here's one that's useful, not as exciting as the one I'll show you next. I just want to show you the function. We'll probably do things with it in section. Here's one that counts the atoms. So in this case here, there are 10 atoms. That's all the leaves, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And how would you do that recursively? Well, you have this function called count atoms. I mean, ignore the two cases, the first cases, but the main point is, the meat of the procedure is you count atoms in the head of the list. I mean, here it makes a little more sense to say car and cooter because it's kind of a left-right. So the left subtree is always accessed by car, the right subtree by cooter. You call count atoms recursively on each of those and add them up. So this just says that when you're in the middle of the tree, and you're looking at how many nodes there are, how many atoms, count the ones on the left, count the ones on the right, and add them together. Now, there are two cases you bottom out. If you give it something that's empty, you return 0. If you give it something that is actually an atom, you return 1. So this is a beautiful little function that traverses the tree and counts the atoms. And if you actually run it on this tree, and I've given you code for that, it will return 10. So this is something, as an exercise, please look at this, try to figure out how it works, try to prove that it's correct, and analyze its complexity. Now, of course, we have to do some things here. What is an atom? Here's, I'm sorry, it's broken over 2 pages. This little predicate here I've written basically says an atom is anything that's not a pair. And that makes all this code work. So now we can look at a complicated object and do things like count up the number of objects, a number of atoms in a number of nodes. What about a more interesting thing? So, you know, if I were to apply map to some creature like this, right, you could do something like take the length of each sublist, or I could, you know, add, you know, take each sublist and add a 44 to it, that kind of thing. But I wouldn't be traversing down into the sublists with map. Like map just basically does the top level, which is great, right? Very useful. What if we wanted to change every primitive, like a new tree with exactly the same shape, but we'd say added 2 or added 1 to each of these elements? So we can write something like map that's called tree map that does that, that traverses these data structures. And here's tree map. And again, you should look at this here. So look what I've done here. I'll show you the usage of this. Here I have a complicated tree, right? It's not the tree I had before. I have this thing like this. So I have this tree here, and it doesn't really even matter how it's configured. It has a 1, the leaves are 1, 2, 3, and 4 with various nestings. When I apply tree map to it with this function here that adds 10 to each node, I get back a new tree with exactly the same shape. It's isomorphic, which means the same shape in mathematics. But look, what I've done is I've added 10 to each node. So instead of 1, 2, 3, 4, I now have 11, 12, 13, 14. How does tree map work? Well, it's a lot like count atoms. You know, if you give it a null tree, it returns the empty tree. If it's an atom, it takes the tree and f's it. That's all it does here. That's all this step does. Otherwise, what do? Well, I cons up a new tree. The left of it is what I get if I call tree map recursively on f and the head. The other side of the tree is what happens if I call f recursively on the tail, tree map recursively on the tail. So this just says, in order to map a function f over every node in a tree, what you want to do is for every node, which is an atom, take the node and f it. In order to construct a new tree, what you're going to do is you're going to take the left tree, which is accessed through head, and you're going to call tree map recursively. You're going to map f recursively over the left subtree. This is going to map f recursively over the right subtree. So what I'd like to leave as a challenge for you all is to think about what we've learned today, which we went through in a lot of detail, and try to understand these more complicated procedures, namely, how can lists represent things like trees? And here's an example here. How can we do simple operations on trees like this, such as count all of the nodes? And how can we write complicated, not complicated, but powerful higher order procedures like tree map that takes a function f and applies it to every node in the tree and returns a new tree that's been appropriately f'd at every node. So that's pretty neat. I wrote wow, and I mean it. So see if you can understand those things. See if you can write code like this. See if you can prove that it's correct. See if you can figure out its complexity. Those are the questions we ask in mathematical computer science. And I think we're going to do some of those in section, or we'll give you some exercises about them. All right, to summarize today, what have we been doing? We did a lot of stuff with list structure, right? So lists are made out of pairs, and basically they're pairs where the tail is a list. The head gives you the first, the tail gives you the rest. In a proper list, repeatedly tailing a non-empty proper list eventually gives you the empty list. And these are kind of the best behaved lists. We went over quotation, which lets you turn off the evaluator, and map, so we take successive tails of a list, building up the results using cons. And then we looked at some fancier things building on those concepts. We looked at append, which puts lists together. We looked at some functions that actually operate on trees. So in addition to the things I've suggested you look at more in detail, I'd like to give you sort of 3 little challenges to think about. So the first is to look at a strange beast like this. Define expression to be a list like the following thing. This is an interesting creature here, right? First element is a symbol called integral. Second element is a list. The third element is a procedure object. Then we have some more.
We lost Dr. Donald, it seems. Hopefully he'll come back in a second.
I'm sorry, did I lose you for a minute there?
Yeah, you're
I'm
back now.
sorry. Yeah, hold on, I'm gonna try to really turn off the phone calls. Sorry about that. All right. All right. I'm very sorry about the technical problems. Apparently when I get a phone call, it messes up Zoom. Am I back and can you hear me?
Yeah, fine.
All right, I'm very sorry about the problems. All right, so the challenge is if you have a strange beast like this expression, can you draw the box and pointer diagram? But also think about types. What's the type of this expression? It's got all this stuff in it. It's kind of could be very useful to make a thing like that. And how would you think about doing this in other languages? So list is very powerful in that the types in a list don't have to be homogeneous. In other words, you don't have to have a list just of integers or a list just of symbols or a list just of strings. You can mix the types between these and get something very powerful. And in fact, that's what code is. So this is worth thinking about as a elementary but nevertheless useful exercise. Second, one thing you can think about here is if you've only used languages like Python and Java, this wouldn't have occurred because those are well designed in this regard. But in other languages, it's possible to have memory leaks or pointers to parts of memory you're not allowed to have. So one thing you can think about in terms of architectural design is how is it that in Scheme, it's impossible for lists to have this bad behavior? In other words, why is it that pointers are always valid? And finally, and perhaps more directly related to the mathematical mission of the class, we have procedures here like copy, and we have append, and we have tree map, and count atoms. How would you go about proving that these procedures on lists and trees are correct? And that will be what we'll be doing in the next few lectures to try to think about good techniques for that. But you actually have the techniques now, you have to kind of structure them in the right way. So, and just to put not too fine a point on it, I made some arguments about these. I drew some box and pointer diagrams. But for append, all I did is prove that append was correct when called with two particular arguments. You'd like to prove that append correctly appended two lists, even when one of them could be rather large. So with that, I want to take a couple of minutes to see if we have questions. And then at the end of class, which will be fairly soon, I will stay around if anyone wants to chat with me or the TAs further. So thanks, that's lists as we see them today. I want to mention that I believe that next week, what I'd like to do is do some proofs for you to solidify your understanding of induction. So I'll try to show you some more induction proofs at the board, so to speak, but more importantly, I'll try to give you some to do in small groups, and then we'll come back and talk about our answers in order to try to do some problems together, even in a big setting like this, so that we can ask questions and make sure that your grasp of induction is continuing to grow and that it will be even firmer. So I'd like to spend next week one or possibly two more of the lecture periods doing proofs with you. And then after that, I'll teach you structural induction in the lecture 12, probably. All right, any questions?
I have a question concerning append. Does it create a new memory location? I don't know, according to the box diagram, it looked like L1 just stays and then like it is hung onto L2. So I'm a bit confused about that.
Yes, well, let's go back. That's a great question. Let's go back and look at the document camera. Just because I have it already written down, which is reasonable. All right. All right, just checking, can you see the document camera? Can you see me?
Yeah, it's working
Good.
out.
Good. All right, so I mean, I animated this, so we're looking at it ex post facto, but remember the inputs to append were L1, which points here, but represents this list, and L2, which points here, represents this list. All of the red boxes are new, they're created by append. So the answer to your question is a little bit hard for me to answer formally because you asked, does it create a new memory location? So that's something that would be hard for me to say yes to because it's not clear whether a cons box is 1 or 2 or how many memory locations. And also, in some sense, it creates 3 of these objects. So I will answer it by saying that append, in this case, created 3 new cons boxes, and it hooked them together in this fashion, and then it returned them. So it creates this cons box, this one, and this one. It hooks them together like this, and it returns a pointer to the first one. And that's the answer, which is the appended list. Does that help?
Yeah, thank you very much. Also, and then, I don't know, hanging on to that, I guess, is it after that, is it, I mean, it's not stored, it's just directly evaluated, right? If you run, I don't know, the append, or yeah, it's stored as a procedure. But is there any way to, this new list, to like quantify it under a new variable, define it under a new variable, sorry, to, yeah, better.
Sure, it's not stored as a procedure at all. That's not correct. Append is a procedure, right?
Oh yeah.
Yeah, so I could do this. I could say define, great question. So before I answer this, let me give you what your expectation should be in this technology. Is unless I tell you otherwise, all values are first-class objects. So they all have the same rights, procedures, and obligations. So you can bind them to variables, you can store them in data structures, you can pass them into functions, you can return them from functions. And that's true of lists as well. So I could define L3 to be append 1, 2, 3. And then notice here, this is supposed to say we return this, but all this would do in this case, I would indeed return this, but now L3 would be bound to this pointer here. Does that make sense? I can use it anywhere I like.
Yeah, perfect. Makes sense. Thank you.
That's good. And again, you know, they're dead horses here and they deserve beating, but notice that I've not changed L1, I've not changed L2, nor have I prevented anyone else from reasoning about L1 or L2 by changing them. So they stay the same. And L2 has no knowledge of L3 and L3 has no knowledge of L2, which is kind of cool. Great questions.
I just had a quick question about the map. Like, so for map,
Sure.
we were talking about complexity. So like, I just was wondering, so what's the difference between, so the first one where we wrote that the complexity was like ON times O of GL versus the one with like the sigma and the GMI less than or equal to.
Great question.
Mm-hmm.
And we can go over that again, or go over it, hopefully not just exactly again, but in a different way. Mm-hmm. So I'm gonna just write some more here. Okay. So let's remember what map does. Good enough?
Mm-hmm.
All right. So we'd like to know the complexity of this. And we had a nice discussion. I think Vanessa said, well, obviously it's linear. And so we have to have some variables here to think about this. It has to traverse the entire list. But it also has to F every element of the list. And so it depends on how long F takes as well. So the observations here, I mean, the point isn't, I think the point here isn't to get the math exactly as I got it. My math is correct, but the point is to understand the concept at this stage. So the key thing is map must traverse L, right? And this means that if L has size n, that takes at least order n work. Is that good?
Mm-hmm. Yeah.
All right. But second, map must apply F each element of L. And you can see that here.
Mm-hmm.
It's going to do that. So our conundrum is how long? And we don't know, because we don't know what f is, right?
Yeah.
So if I were to have an oracle that said to me, the answer, I'm going to cross this, the answer was it took time, you know, just let's say time y. We don't know what y is. Then our complexity in some sense would be something like order n times y, right?
Yeah. Mm-hmm.
But the problem is we don't know what y is, and we don't know if y is dependent on n. We don't know if y is independent of n, and so forth. So think of our example here where we said map length over a bunch of lists. And of course, we'd expect this to return the list 1, 2, 3, and 10 to the 10th minus 7, right?
Mm-hmm.
So obviously the length really, really matters, right? It's going to take longer for these things. Now, the key thing to realize in setting this up in this example is that if we call the length of one of these lists, let's call the element here L sub I. This is like L sub 3. This would be like L sub 4, right?
Yeah.
The key thing here is that the size of L sub 3 and L sub 4 is completely independent of n. It's a different variable. So this is something we haven't really seen before, is that the complexity is going to depend on 2 independent variables. One has to do, well, 3 independent variables. One is what's n. The second is how long, how big are the things in the list? And the third is how long does f take on a thing of that big? Does that make sense?
Yeah.
So look at length here. You know, length, I mean, some people might think length should take constant time or quadratic time. It doesn't really matter what they think. But the point is it takes different amount of time. So there are basically 3, you know, if you ask the complexity, there are 3 things you have to know. You have to know what is n, and what is m. So call this M3 is the size of L3,
mm-hmm.
and M4 is the size of L4. So you need to know n, you need to know M1 up to Mn,
Mm-hmm.
and you need to know that, you know, f is order g, right? F runs in time order g, so to speak, right? You have to know the complexity of f in some sense.
Yeah.
And in this case, it's linear in some sense. Now, so what I said is, well, you might not know the sizes of these things, but you might know the max. So one thing you might have here, you might have a big M here and say that's equal to max over I equals 1 to n of m sub I. So take the biggest one.
Mm-hmm.
And in that case, we could write the complexity as n times g of big M, order that, right? So this kind of started to make sense, right? We have the number of elements in the list. Well, that's a natural measure of complexity. And then M is the largest thing in the list. So this is a bound on the running time of the algorithms. That's pretty good. So an example would be length. We have g of n equals order n. Let's call that m instead. So that would, in this case, reduce to order n times m, right? Something like that? Yeah. So kind of quadratic time. But the thing I wanted to mention is that the max may not be a good estimate. Like, look, in this case here, we have 3 things, very small, and one really huge one. What's the real running time? I mean, it's hard to say. So the point is to realize this is an upper bound. I'll denote that by this. And the real complexity, if you knew something fine-grained like this, would be the sum for I equals 1 to n of g applied to each of the mi. So no one writes complexities like this except as an intermediate step, because no one could stand it and can't compare it. This is what you're doing, is you're taking I mean, you have n of these, you take f and you apply it to each element that takes g of mi time for element I. Kind of a nasty thing. So computer science trick and mathematician trick. Well, look at the biggest one I get about. Biggest one is m. I get something like this. So the key point here, remember our example of mapping length over a bunch of things. What we have to do is we have to realize that yes, it's linear in the size of the list, which in this case is 4, but the complexity also depends on the complexity of length as a function of its input. The size of its inputs can vary between 1 and a quadrillion in this case, or actually 10 billion. Does that make sense? Yeah, it's a kind of elaborate example, but I just wanted to indicate that just saying that it depends on the two things doesn't mean we naturally get a very good complexity. So I think the way to think about this is, think of map as always being linear, but if you want to take f and you want to f a bunch of things in a list where f is super expensive, as those things get bigger, then your function will take longer, and you can calculate what that is.
Mm-hmm.
Is that helpful?
Yeah.
Mm-hmm. Absolutely.
Thank you.
Sure.
Hey, I have a question about the exercise 1 that you left us off at after the today's stuff section.
Sure.
Is it possible that you could just walk through the pointer and box diagram for that? Because I want to make sure that I did it correctly.
I would be happy to do that. Let's see. And is it true that I did it correctly? Is that good? I got it? I don't have to answer yet. That's setting it up, right?
Yeah, that's it. That's it.
Okay, good. All right, so we're going to call list, and it looks to me like we have 1, 2, 3, 4, 5. What? 1, 2, 3, 4, 5, 6, 7. It's going to make a list of size 7 at the top level. So. And I return a pointer to that. Is that what you got, or did I mess up?
That's also what I got. Although I do have a question. What exactly does integral and like of the function, like what do those represent? Are there strings to?
The scheme does have strings, but they're kind of unnatural. So these are actually called symbols, or they think of them as variable names or symbols, although they're not bound to anything. So we covered them a little bit in the first or second lecture. So they're basically things that could be used as names. So if you said integral and evaluated this, you get back integral. So they're not strings per se. You can convert back and forth between them. They're really what are called symbols. And I guess one way to think about them is there are things you could use as a variable name. So I could say, if I wanted to define integral, I could, we did this before. I actually said lambda, f, a, b, and so forth. Or I could define, 2 to be 0.0. They could have values. Does that make sense?
Yeah, so if you tried to say integral was just a symbol that was like not bound to anything, so it wasn't defined. If you tried to evaluate the second integral you have there that doesn't have the quotation in front of it, that would return undefined, correct?
In a sense. So let's see what happened. What would happen if I did, so as I said expression, which is this thing here, and suppose I then said car of the expression, what would this return?
That would return the symbol integral, correct?
Right. Totally correct. Now, if I were to then evaluate that, now you haven't really learned the eval function yet, because technically the eval function also requires an environment, but if you did this, this would give you an error because it's not defined. Actually, it might give you an error. It depends on whether it was previously defined. Suppose here I said define, suppose I put my define integral statement up here, right? So eval always is going to evaluate things. It might give you an error or it might give you some procedure. Depends on whether or not you've defined it. So in, tabula rasa, in this situation here, it absolutely is going to depend on the environment. So if I've already defined integral like this, it's going to evaluate it, give you back the procedure. If I haven't defined it, get an error. So it's a symbol just like X. So you can sort of see this a little bit even in this lecture. I said, what happens when you evaluate X? Well, it depends. It could be an error. It could be whatever X is bound to, like 6. But when I say quote X, I always get X back.
Okay, that's exactly what I was looking for. Thank you.
Yeah, sure, absolutely.